So now we are dealing with a very important concept, and that is the gravitational force. You can think of the Earth acting on a mass, or you can think of the Sun acting on a planet, whichever you prefer. But that's what I want to deal with when the distances are now very large. Let me first give you the formal definition of gravitational potential energy. The formal definition is that the gravitational potential energy at a point P is the work that I, Walter Lewin, have to do to bring that mass from infinity to that point P. Now you may say that's very strange that in physics there are definitions where Walter Lewin comes in. Well, we can change it to gravity, because my force is always the same force as gravity with a minus sign. So it's also minus the work that gravity does when the object moves from infinity to that point P. I just like to think of it, it's easier for me to think of it as the work that I do. So if we apply that concept, then we first have to know what is the gravitational force. If this is an object capital M, and you can think of this as being the Earth if you want to, and there is here an object little m, then I have to know what the forces are between the two. And this now is Newton's universal law of gravity, which he postulated. Universal law of gravity. He says the force that little m experiences, this force, equals, I'll put a little m here and a capital M here, so it is little m experiences that force due to the presence of capital M, equals little m times capital M times a constant, which Newton in his days didn't know yet what that value was, divided by r squared, if r is the distance between the two. This object, since Newton's third law holds, action equals minus reaction, this force, which is, I will indicate it as capital M, little m, it is the force that this one experiences due to the presence of this one, is exactly the same in magnitude, but opposite in direction. And that is the universal law of gravity. Gravity is always attractive. Gravity sucks, that's the way to think of it. It always attracts. There is no such thing as repelling forces. The gravitational constant G is an extremely low number, 6.67 times 10 to the minus 11 in our SI units, which is Newton's square meters per kilogram or something like that. That's an extremely low number. It means that if I have two objects which are each 1 kilogram, which are about 1 meter apart, which I have now here, about 1 meter, that the force which they attract each other is only 6.67 times 10 to the minus 11 newtons. That is an extremely small force. If this were the Earth, and I am here, and this is my mass, then I experience a force which is given by this equation. This would be then the mass of the Earth. Now F equals ma. So if I'm here, I experience a gravitational acceleration. And the gravitational acceleration that I experience is therefore given by mg divided by r squared. And so you see that the gravitational acceleration that I experience at different distances from the Earth, or for that matter at different distances from the Sun, is inversely proportional with r squared. We have discussed that earlier when we dealt with the planets and we dealt with uniform circular motions and we evaluated the centripetal acceleration. We came exactly to that conclusion, that the gravitational acceleration falls off as 1 over r squared. 10 times further away, the gravitational acceleration is down by a factor of 100. If you are standing near the surface of the Earth, then of course the force that I will experience is my mass times the mass of the Earth times the gravitational constant divided by the radius of the Earth squared, just like we are here in 26/100. And so this must be mg. That's the gravitational acceleration if we drop an object here. And so you see that this now is our famous g, and that is the famous 9.8. If you substitute in there the mass of the Earth, which is 6 times 10 to the 24 kilograms, you put in here the gravitational constant, and you put in the radius of the Earth, which is 6,400 kilometers, out pops our well-known number of 9.8 meters per second squared.